Gaussian process regressors, or simply GPRs, are quite amazing when it comes to regression models for prediction and in fact also for optimization. They are non-parametric, capture uncertainty in the data, and have proven successful in many applications. In this video, we will implement a GPR in Python, actually in a Jupyter notebook, using numpy only with interactive visualizations of the kernel, the GPR, the random functions, how the GPR adapts to new observations, and its response when parameters like noise and length of the kernel change. For our GPR, we are only going to use numpy for our linear algebra operations and plotly to visualize our results. I already implemented a couple of helper functions in order to plot quite quickly. So this one is for updating the layout of our figure. This one is for plotting our functions, in our case the mean. This one is for plotting our data points. And this one is to visualize the uncertainty as an area in our graph. And I already wrote down a couple of formulas we are going to use because, well, they are quite difficult to remember. So this one is the formula for the squared exponential kernel, and this one is the formula for adapting our multivariate normal distribution according to points we have observed. So that's it. Let's start. So first thing we're going to do is to implement our covariance function. So in our case, this will be the squared exponential kernel. So for the squared exponential kernel, when initializing it, we need two parameters, namely the length scale, which is a float and greater than 0, and the signal variance, which is also a float and greater than 0. Okay, next thing, when we have initialized our squared exponential kernel, we want to call it to two arguments. And what we're going to do is we simply return this formula here. Let us quickly visualize the squared exponential kernel. Okay, let's see if this works. What I will do now is I will add some default values in our squared exponential kernel. So by default, I will set the length as well as the sigma both to 1. And yeah, I have to compile it and let's see if it works now. So what I plotted here is the squared exponential kernel with the second argument, in our case, fixed to 0. And I'm varying over the first argument. So from -10 to 10, I'm varying this argument in the squared exponential kernel. So this is the argument here. And well, I implemented some widgets. So what we can do now is we can see what happens when we're changing, for example, the second argument. So let's see what happens when we change the second argument to -4.3, where what we see is we are just shifting the graph on the x-axis. So let's see, this is perhaps more interesting, what happens when we are changing the length. Cool. Okay, now that we have implemented our squared exponential kernel, we are ready to implement our GPR. So let's do so. Let's simply call it GPR. So let's see, when we're initializing a GPR, what we need to give it is our already observed points. So there we have, for example, data x, which is the input of the points we have observed, and the output of the points we have observed, which we call data y. Then we have to give the GPR a covariance function, which by default we are going to set as an instance of the squared exponential kernel. And this is pretty cool about GPRs. We can include a noise in the data we have observed. So this is what we are calling noise or white noise. And what we're also going to do is we are giving this GPR a memory variable where we store, in the end, when we did predictions, then we store the mean, the covariance matrix, etc. in the self.memory. And for now, we are going to set it to none. Okay, let's have a look at the formula. So as you see here, for the formula to adapt the multivariate normal distribution, we need to calculate a couple of matrices. And the entries of those matrices are all just the covariance function applied to our data. So let's quickly implement a helper function which calculates all of those. So the k lower star, and k lower star. Okay, so now we can compute those k and k lower star and k lower star with this helper function here. And yeah, as we observed in this formula here, for each prediction, we are going to use this matrix k. And this matrix k is not dependent on our values where we want to do predictions. So this matrix k is just the covariance matrix of the data points we already have observed. And since we are going to use this in every prediction, we are going to calculate this when initializing a GPR. And here, I forgot, we need to add on the diagonal the noise. So, and what we are going to do for stability reasons is we're going to add a value which is a little greater than the so-called machine epsilon. So because when we are dealing with matrix operations, we have some numerical instabilities in our operations. In order to prevent the covariance matrix from being non-invertible, from being singular, we are adding those values on the diagonal. So, and in our case, this is something about 1.6 e to the -7. So we are adding 3. I mean, this is a pretty small value, so this will not make any difference when visualizing our GPR. But I mean, you can try to leave it out, but you will most certainly run into some errors. But do so. Okay. So now that we have initialized our GPR, where we want to define a predict function. I mean, we want to do predictions with our GPR, and we want to do this at some values. And in this predict function, we basically implement the formula above. So this left side in the formula here will be our adaptive mean. And this is what we're going to return as our prediction. And on the other hand, we have this adapted covariance matrix in which we have our variances. So we need to calculate both of them. So let's do so. We need to calculate this k lower star and lower star star first. So this is simply the covariance matrix. Oh, above here, I forgot the covariance function. This is simply the covariance matrix of the input data and the add values data, and well, with the covariance function we specified when initializing the GPR. So, and we're going to do the same with the lower star 2, but in this case, both of the data here are at values. Okay, so now we have the inverse of k, of the covariance matrix of our input data, and of the data with the values we want to do predictions on, and the covariance matrix only of the data we want to do predictions on. So let's implement this formula here. Oh, I forgot. I mean, this is the covariance matrix, okay, but we want not to save the covariance matrix, but we want to save the inverse of the covariance matrix. So I forgot this here. Okay, so this is our mean. Let's implement our covariance covariance matrix. Yeah, okay, covariance matrix. Let's call this here adapted, so we can distinguish it from our. I mean, maybe this is not the perfect name, so this should like contain give back the covariance matrix. So we should have defined this as give calculate covariance matrix, for example. So maybe we can adapt this here. So now we have the correct name, and now we can really name our covariance matrix as covariance matrix. So let's have a look at the formula, what we need to do. Okay, so k lower star minus k lower star times k to the minus 1 times k lower star transposed plus our noise on, well, I guess this formula is a little bit wrong here. This shouldn't be at this stage, but this should be here. Okay, now the formula is correct. Okay, so covariance matrix. Okay, that's it. So we have calculated the mean and the covariance matrix. And what we're also going to calculate is, well, the variance. So this is simply the diagonal of the covariance matrix. Okay, now we're going to store all of those information, so the mean, the covariance matrix, and the variance in our self.memory. And what we're going to return is, well, the mean. Okay, so that's it. This is a GPR. It's not that hard, isn't it? Let's see if this works and if we can visualize this. Yeah, I see there's line 6. So we have to set the noise by default. So let's set it to 0 by default. I mean, this is reasonable since in most cases we won't expecting noise in our data points. So this should work now. Okay. And now let's simply implement a function where we can visualize our results. Okay, so I implemented a couple of functions where we can plot our GPR now, and I ran into some errors. So the error happened here. I forgot to call the inverse method of this linarc module. So you need to add this. And then I initialized a couple of values here. So x values, let's call this visualization. Okay, so I defined a couple of values. So this is really random. You can change those as you like. And here I defined where we want to do predictions in order to plot our predictions. And this is a helper function for plotting our GPR. Well, I mean, we're often going to use this function, so I put it into a function. And let's see if this works now. So this works here. So here you see the red ones are our observed points. So those are the ones which I specified above. And well, the blue one is the mean of our GPR. And the gray scales, the gray area here are the uncertainty areas. So as you see here, this one is the first uncertainty area where where I just added, respectively subtracted 1 times the standard deviation of the mean. So the Gaussian process regressor, as we implemented above, works. So let's do some cool stuff with it in order to see what happens when we are changing some parameters in the kernel, or for example, draw random functions from our Gaussian process regressor. So first thing we're going to do is we will implement a plotting function where we can add random drawings from our GPR. So remember that a GPR is sort of a probability measurement over functions. So this means that we in particular can draw random functions from our probability distribution. So here I implemented that we can visualize a random drawing from our GPR. Let's see if this works. Okay, so here you see our observed points. And when I press the button add random drawing, well, we add a random drawing. So this blue line here is the mean of, sorry, it's not the mean. It is a random drawing from our GPR. So it is in some sense a random function. So we can do this again and again and again. And what you are observing here is that the density of when we're adding more and more functions corresponds to the grayscales in our GPR with mean and standard deviation. Yeah, I mean, how we interpret this is that most of our random drawings or random functions are in those uncertainty areas here. And the mean over all of those functions is the blue line here. So I mean, this should be the result when we add infinitely many random drawings here, and we see it is. Okay, so for the next thing, we want to see what happens when we iteratively add points to our GPR. So what happens when we train a GPR or initiate a GPR with one observation, and what happens, how it looks like when we're adding more and more observations. So let's do this here. Okay, let's see if this works. Okay, very nice. So what we're seeing here is I just gave our GPR 1 observed points, and this is the result when initiating this GPR with this 1 observed point. So let's see what happens when we add more data points. This is very nice. I like it. I like to see how the GPR adapts to new data points. We're going to do something very interesting now. As you observed above, in our covariance function, so in our case in the squared exponential kernel, we have 2 free parameters, yeah, namely the length and the sigma. So here it is. So we can vary the length, and we also have the sigma f, which is also a free parameter. And also in our GPR, we included the white noise. So this is also a free parameter. Yeah, the noise is the noise which would we expect in data points we observe. So we have, in our situation, free parameters. So, and now we raise the question, what happens, how does the GPR looks like when we are changing those parameters? And this is the next thing we want to visualize. So we want to visualize a plot where we can change with a slider the sigma, the white noise, and the length. Let's do so. Okay, so I implemented this here. Let's see if this works. Cool, so you see here, this is a Gaussian process regressor with noise equal to 0.1, length of the squared exponential kernel equal to 0.5, and the sigma in the squared exponential kernel equal to 1. And in this plot you see, I mean, the blue line is, as always, the mean. So this is our predicted function, and the red points are our observed points, and these gray areas are our uncertainty areas. And as you see here, our mean function does not go right through our observed points. And I mean, this is due to the noise we expect or we have specified in our data points, which is not 0. So when we are turning this to 0, we would expect our function to go right through our data points. Let's do so. Yeah, and I mean, this is what we see when we put the noise to 0. And now we can also vary the length rate and the sigma. So yeah, let's put in some extremes. So let's put the length to 0 or almost 0 and sigma almost to 0. And as you see, I mean, I believe this is quite crazy that a Gaussian regressor can take so many different shapes of functions with only three parameters. So let's see what happens when we are putting the noise to the maximum and the length to the maximum and the sigma to the maximum we specified here. And as you see, I mean, when we expect very high noise in our data, then the function we get in return is almost constant. Okay, so now we have implemented a graph where we can change our three parameters. And now I will leave you with this one question, namely, when we have three parameters, what are the best parameters, the best suited for our problem here? And the answer to this we will give in the next video.